Okay, so now our application. It says the path of a projectile that is launched with an initial velocity v naught from a height of h feet above the ground and at an angle theta with the horizontal is given by the parametric equations. And so these are generic based on different velocities. That's our initial velocity and different angles. So x is v naught cosine theta t and y is h plus v naught sine theta t minus 16t squared. T is time in seconds after the launch, so that should be bigger than or equal to 0. So I have a specific situation graphed here. Here a baseball was hit with initial velocity of 120 feet per second and an angle of 30 degrees with the horizontal. The ball was hit at a height of 3 feet off the ground. So that is, right, the 3 is our h here. So for part A, find parametric equations that describe the position of the ball as a function of time. So we're just going to use these and plug in all of the parts that we know. So part A, we have x is v naught cosine t, or cosine theta, excuse me, times t. So v naught is 120 feet per second, and theta is 30 degrees. So 120 cosine of 30 degrees times t. 120 times cosine of 30 degrees is the square root of 3 over 2 times t. So that's 60 square root of 3 times t is for x. And y is, so h plus v naught sine theta times t minus 16t squared. H is 3 plus 120 cosine, or excuse me, sine 30 degrees. T minus 16t squared. So 3 plus 120 times 1/2 t minus 16t squared. 3 plus 60t minus 16t squared. So our equations, x equals 60 square root of 3t, y equals, this y is quadratic, so maybe you want to write the first term, the t squared term first. There's our parametric equations. And whoops, I'm sorry, that got a little blurry there. No, that shouldn't happen. I forgot what I was going to say. Well, I guess that's all I was going to say. T is bigger than or equal to 0, so well, we can see what the restrictions are for x and y on the graph here. X goes from 0 to whatever this number is, and then y goes from 0 to whatever the max height is here. So we won't put any restrictions on this yet. We have to get more information. So B, describe the ball's position after 1 second and 3 seconds. We're just going to plug t into these equations to get the answer for part B. So let me move this up here. For B, when t equals 1 second, we have x is 60 square root of 3, and then y is negative 16 plus 60 plus 3, right? T is 1. So 63 minus 16 is 47. So this is, sorry, let me go back. This is all in feet. So what this is saying is the ball, the coordinates are 60 square root of 3. Let me get an approximation for that, which is approximately 103.9 feet. Oops. Sorry, I wrote that on the wrong page. So the ball has horizontally traveled about 103.9 feet, just a little bit more than 100, and vertically it's 47 feet high. So we're talking about this point right here. This would be for t equals 3 seconds. That's what the first, I don't know why that focus keeps doing that. It's supposed to be locked. Sorry. Okay, so this is the height here. Y is the height. And then this is how far it's traveled vertically. Okay, let's do it again for t equals 3 seconds. So now we're going to plug in 3. X is 60 square root of 3 times 3. And we'll approximate that again. It's a little easier to understand. So about 311.8 feet. And then y equals negative 16. 3 squared is 9. Plus 60 times 3 plus 3. Oh, well, I won't have to approximate that one. 16 times 9 plus 180 plus 3 is 39 feet. So at 3 seconds, vertically the ball has traveled 311.8 feet, about here, and it's 39 feet high. So probably about right here. That's for t equals, I don't know why, what the world, this is for 1 second. This is 3 seconds. Okay, that's what's going on there. Now in question C says what's the maximum height attained by the ball? So C, we want to, the height is the y equation, right? So y equals negative 16t squared plus 60t plus 3 gives the height. So we want to maximize this equation. And it's a quadratic equation, so we have to think back to what we did in college algebra. And that is, when we maximize a quadratic, we need to find the vertex. And this does open down because of the negative 16. So we're going to find the vertex. Oh, this is a little review here. The first coordinate, which in this case is the t coordinate, is equal to negative b over 2a. That'll give us the time when this object reaches, or this projectile reaches its maximum height. So this is negative 60 over 2 times negative 16. 60 over 32 is 1.875 seconds. And so now we need to plug that into the equation to find the max height. So y at 1.875 is negative 16 times 1.875 squared plus 60 times 1.875 plus 3. And I'll just put that in my calculator. Plus 60 times 1.875 plus 3. So 59.25 feet is the maximum height of the ball, or projectile. All right, let's look at the graph. The max height is about here, and that seems like a reasonable answer, right? 59.25. All right, question D, how long is the ball in the air? Well, the ball is in the air until it hits the ground. It hits the ground when the height is 0. So for D, what is t when h, our height, I'll say, which is y, equals 0? So this means we need to solve the quadratic equation, negative 16t squared plus 60t plus 3 equals 0. And I'll use the quadratic formula. T equals negative b would be negative c Oh, you know what? I don't like it when a is negative. Let's multiply everything by -1. So 16t squared minus 60t minus 3 equals 0 will give us the same solution. We just don't have to divide by negative then. So we'll make this negative b will become negative 60 is plus 60, plus or minus the square root of negative 60 squared minus 4 times positive 16 times negative 3 all over 2 times 16. So let's see what the discriminant is. So 60 squared plus 12 times 16. So we get 60 plus or minus the square root of 3,792 over 32. So the square root of this number is about 61.6. So you can see if you subtract that, you're going to get a negative answer. Well, we only want the positive answer. T has to be bigger than or equal to 0. So we will use, I'm sorry, I was way off the screen there. T equals 60 plus the square root of 3,792 over 32. So plus, whoops, that's not 60, there's 60. Divided by 32. So that's approximately 3.8 seconds. At 3.8 seconds. All right, one more question, and that's how far did the ball travel? Well, the ball traveled for about 3.8 seconds, so let's just approximate. We can see it's going to be less than 400, right? The ball travels x equals 60 square root of 3t, and t is about 3.8 seconds. So I think I'll just plug this in here. So for E, x equals 60 square root of 3t, and t equals 3.8 seconds. So that implies x equals 60 square root of 3 times 3.8. Which is approximately 100. Oh, whoops, that doesn't make sense. I kind of know the answer is close to 400, right? That doesn't make sense. I accidentally put plus instead of times. So let's do 3.799 times 60 square root of 3. So that seems more reasonable. About 394.8. That agrees with our graph for part E. Right, and the graph is on the other side. Yeah. So that seems like the right answer. We got the right answer. Okay, that problem obviously a pretty lengthy one there, but it's a good example of where we would use parametric equations, because we can map the flight of the ball in this case. I kept saying projectile, but it was a baseball, right? As functions of time, excuse me.